Hi there, in this video we're going to look at sets and functions. So we'll start off with sets. So I could say that 4, and that funny E sign says is a member. So 4 is a member of the set numbers 1, 2, 3 and 4. So if it's in curly brackets, that signifies a set. These are the elements of the set, and they're all separated by commas, and that just tells us that 4 is a member of this set here. So we could also say that 5 is not a member of the set 1, 2, 7. We can also write the empty set just with your curly brackets with nothing in it, so that's the empty set. Now you would have seen all this sort of stuff before, it's just a quick recap. And we can also write, if we had the set A with elements 1, 2, and the set B with elements say 1, 2, 3, then we can say that the set A is a subset of the set B, so that's a sign for a subset, and you can draw that out as well. If we draw a little Venn diagram, then if this is the set B, okay, so the set B has got 1, 2 and 3 in it, then the set A has got 1 and 2 in it, so that there would be the set A. So the set A is a subset of the set B. Okay. Now we could also look and see if we had a set, say A equals 1, 2, 5, and B was the set 1, 2, 7, then we could say that A, and that sign there is intersection, so A intersection B would be all of the elements of A that are in the common to the set B. So the things that are common are 1 and 2, so that would be the set 1, 2, and again you could draw that out in the Venn diagram. If this is the set A, then we would have a set B here. In this instance here, B, there would be a 7 here, and the A, there would be a 5 here. But both sets have the numbers 1 and 2 in common, so you could have a 1 and a 2 in common. Okay, so this is the intersection. Okay, so a quick recap as well on the number system. Now, the set of natural numbers n equals all the numbers 1, 2, 3, 4 off to infinity, and the set of whole numbers is the set of natural numbers with a 0 added, so 0, 1, 2, 3, 4 off to infinity, and the set of integers is the whole numbers but including all the negatives as well, so say -2, -1, 0, 1, 2, and the set Q, the set of fractions which are called the rational numbers, so I'll just write that as a set of rationals, okay, and then you have the real numbers, which are all the rationals and every other number in between, so it's the whole of the real number line, so we just call that real numbers. And we can say then that the natural numbers are a subset of the whole numbers, which are a subset of the integers, which are a subset of the rationals, which are a subset of the reals. So again, in the Venn diagram you can draw out your circles. So that would be your natural numbers, okay, so your natural numbers and your whole numbers and your integers, your rationals and your real numbers. Okay, so that's really just a little recap. Now, one example here to read out and how sets are written out. So you might have something that says, for example, P equals the set of elements X such that, say, X is greater than 5 and less than 10, and X is a member of the set of whole numbers. So that's that W. Okay, so that just reads again, P equals the set of all elements X such that X is greater than 5 and less than 10, and X is a member of the whole numbers. Okay, X is a whole number. Okay, so that's just a quick recap there. Now we'll move on and really want to look at the interesting part of it. We're looking at functions. Now functions are an important part of mathematics, and we've got a very particular description of what a function is. So we'll look at it in two ways. We'll look at it in terms of I suppose really our little Venn diagrams. So if we had our set here, and that's a set X, so we'll say that's a set X, and we've got another set Y. Okay, it's a set Y. Now what a function does, a function maps the elements from one set X onto another set, which we call here Y. So let's put some elements in here. Okay, there's some elements there, there's some elements there. But a function is a very particular about the way it maps. So a function maps from a set X to only one element in the set Y. Okay, so I'll write that out again. I'll write that actually out. I'll say function maps a set, say, X to only one element in a set Y. Okay, so that's important. A function maps a set, maps the elements of a set X to only one element in a set Y. So for example, I'll draw these in. If I went and drew a line from here to there, from there to there, say there over to there, and there over to there, then that is a function. Okay, and we can call, let's say that, call that function f. So that is a function. But if we were to draw something out like this here, 1 2 3 1 2 3, and that's X, and we call that Y, then if we say map this over to here and this over to there and that to there, okay, and say this back to here, then that isn't a function, because in this instance here, this value of X has mapped to two values of Y. Okay, so that is not a function. So let's have a wee look, and we'll see it on our drawing package here, and we'll see it a bit better than here. Let's have a look and see if I can find it. Oh, there we go. So let's get rid of these. So let's draw out a function. So I can say Y equals, say, X squared. Now Y equals X squared is a function because for each value of X there's a one and only one value of y. So if I come along 1, I go up to 1. If I come along 2, I go up to 4. If I come along 3, up to 9. If I go to minus 2, I go up to 4. Okay, minus 3, I go up to 9. So for each value x, there is a unique value for in the y-axis. Okay, so that is a function. Now let's draw something out that it's not a function. So if I had, say, x squared, whoop, that's not quite right, x squared plus y squared equals r squared. Okay, so let's just draw this in. So there's the value of r. So that there draws out a circle and it's got a radius of the value of r. Now that isn't a function, not in the sense that we have defined what our function is, because in this instance here, for each value of x, we don't have a unique value of y. We've got two different values of y, so we can come along 2, and we're going up here about, what is that, 2.2, okay, and we can also come down the way, minus 2.2. So for each value of x here, I've got two values of y. That's not allowed, okay, and again in the negative side here, each value of x, I've got two values of y. It's not allowed, so that is not a function. So now what we're interested in as well is the next section here is the composition of functions. So let's have a look, and we'll go back in and we'll look at the composition of functions. Now the idea about composition of functions is that we can go from one set here, which say we call it the set A, and we can go from the set A to the set B via some function. So we'll call that function f. Then what we could do is we could then go from the set B and we could go to another set, which is set C, and we go there via another function which we call G. Okay, so we can go from A to B and then B to C. But what we could also do is we can compose these two jumps, okay? We can compose them into just one single jump. So rather than going from here to here to here, we can go straight from here to here via a different function which we can call h. Now we've got to try and find out what that function h is. Now we'll go through it, and we'll go through an example first, and then we can go and have a wee look at it on the drawing package. So let's say we've got f of x, say is x squared, and then g of x equals x minus 1. So what would happen is, if we take a value for f, say let's say the value of f is 2, so if we go from 2, we would go 2 squared, which is 4. So now we're at point B, we're at 4, and we're going to say 4, to get from B to C we do x minus 1, so it's going to be 4 minus 1, which will give us a value of 3. So that means that to get from A to C we go 2 to 4 to 3, and we go through both these functions. But what we want to do is we want to find a function here, h, that allows us to just go from this point here to this point here, so it's equivalent to doing both of these. Okay, so now what we can do is, what we want to do is we want to find a function f of x, so that's a function f of x here. I've not put the x in, but because it's understood it's a function of x, and it's g is a function of x as well. Okay, so we want to do f of x first, and then we want to do g of x. So we write that out as we want to do f of x, and then we can put a bracket around and we can put a g there. Okay, so that just tells you want to do f of x and first, and then you want to do g next. Now you'll see that written out as g after f. So that says we want to do g after f. We want to do f first and then g next. So that and that are equivalent. Okay, so you can remember that little right up there. Okay, now in order to do that, let's see if I've got space, just enough space here I think to squeeze that in. So what you're going to do is f of x first. So what is f of x? F of x is x squared. Okay, so you're putting a value in for x and then you're squaring it to get another value. But then what you want to do is you want to do the g next. Okay, so the value for our x has then been passed on to this value here. So 2 goes to 4. So now we want to pass this value in here. So we wanted to pass the whole function here into this function here. So what we're going to do is we're passing this whole function. So where we see an x, we're going to replace it with the entire previous function. Okay, so the entire previous function here is x squared. So we're just replacing this x here with this x squared. So it's a replacement. We're putting this one here into this one here. So we get our x squared, and then the whole thing is still just minus 1. Okay, so that is our h of x, which equals x squared minus 1. So that's our g after f, or equivalent we can say that's our g of our f of x. Okay, so this is our composite function here, the one we've been looking for. Now we'll just figure out and see whether that works. So we can check it with a value. So if this works, then 2 should go to 3. So let's check and see if it does. So we'll write it out here. So h equals x squared minus 1. Okay, so the h of x is x squared minus 1. So 2 squared is 4 minus 1, which is 3. So it seems to be working. It's worked for that one anyway. Okay, so this function here is equivalent to doing both of these functions. So let's have a wee look at it, and we'll see it become more apparent whenever you look at it in the little drawing package here. So let's bring this back up, and we'll get rid of this here, and we'll put in our function. So we'll have our f of x equals x squared. Okay, so that's f of x equals x squared. So we can put a value of, say, what was it, 2. So put a value of 2 in, and we get a value of 4, which is just our x squared. Okay, now what we can do then is put our next part of the function is g. So g equals x minus 1. Okay, oh, a bit of this. G of x equals x minus 1. Okay, so we're doing the red one first, and then we're doing the blue one. Okay, so maybe turn that off. So we do the red one first. So we go 2 takes me up to 4. Okay, and then that 4 then becomes a new value for our x-axis, and then we're going through this one here. Okay, so our 4 will go up to here, and when we go put our 4 through this function, we get a value of 3. So I'll do that once more. We go to our value 2, and then we go through our first function, which is f, which takes us to 4, and then we go along to our value of 4, and we go through our second function, which is our g, which is blue, and that takes us to 3. Okay, so now this here, these are our two functions, and we are saying that these two functions are equivalent to just having one function, h of x, which equals x squared minus 1. Okay, so these are equivalent to just this single function. So take these off just to unclutter it. So that's our final function there. So when we put in 2, we should get a value of 3, which we do. We put in a 2 there, we get a value of 3. Now I'll read this over again with all of them in it. Maybe look a wee bit cluttered, but we'll try it. So again, we do the red one and the blue one, and then we'll compare it to the green one. So we do the red one, so we go to 2, we go up through the red one to 4, and then we go along to 4, we get to the blue, go to the blue one, which is a g of x, and that gives us a 3. Or we can go through the single green one here, and we can say our value of 2 goes through this green function here, which gives a value of 3. So this here is a composite, the green one is a composite function of the red one and the blue one. Okay, now another way of kind of looking at that there, the way I tend to look at it whenever I get confused, okay, is if I bring it back to our little drawing package here. That's the drawing package here. I'll go on to the next page here. Okay, so the way I kind of look at it, I quickly think to myself, I think it in terms of 3 little graphs. So I say, that's x, and that maps to, that's of some function f of x. It's just some random function that takes x and maps it to this axis here, okay, and that's the function f of x. And then what we do is we're then taking this value here of our f of x, which becomes our new line here. Okay, so you can say x goes to f of x, and then you could really kind of say, I think of f of x then goes up to our g of x. Okay, so we're going to go from x to f of x to f of x to g of x, and finally we could write it the other way around. We can say that we could go straight from x here to our function h of x. Okay, so we could go straight from x here through this axis, through this function, and then through another function g, okay, and we could have got through it in one step. Instead of going through these 2 steps here, we can go through in a single step here, x to h of x. Okay, so this one here is a composition of these 2. So you're really, in effect, you could see these axis swapping, so that becomes x becomes f of x, and the value of f of x becomes the new value of this axis here, and then you put that new value in through this second function g of x. Okay, or equivalently you can do one single composition of both of these, g of x and f of x, which takes our x through straight through to this value, or h of x. Okay, so that's really a kind of little graphical way I kind of think about these composition functions. Now the best thing to do is to do some examples, so we will go on in the example sections to go through here, and you'll see some examples getting done. So remember, we could also have things like, so you could have g after f, you could have f after g, you could have f after f, and you could have say g after g. So there's lots of different ways of composing these functions. Okay, so we'll see it better whenever we go through and do a few examples. So that's all there is really there at the moment for this composition of functions. Now we're going to look at say inverse functions. Okay, so now the idea of a inverse of a function is that if we had a set A and we had a set B, then a function, say f, will take us from the set A, okay, to the set B. Now the inverse of that would be a function that would take us from the set B to the set A. So we're looking to go back the way again. Okay, now we write that down as f, and it's a little minus 1. So that there tells us it's an inverse Okay, so that's called the inverse function. So one thing that you have to note though is that in order for there to be an inverse, each element in the set A has to have one unique element of the set B, and each element in the set B has to have one unique element in the set A, okay, before there's an inverse. That's a bit of a mouthful, but we can draw it out and then we'll see it whenever we put it into the little drawing package as well, and it'll become quite clear. So if we had our set A and our set B, so if we had each element here had it mapped to one unique element, so each element A maps to one unique element in B, okay, and also in this instance here, each element in B will map back to one unique element in A, then this here, function f, it will have an inverse, okay, and it will be that function f inverse. Now there will be the possibility of this kind of thing occurring, so we have A and B, so this thing here, we could have a 1, 2, say 3 there, and these 3 here, okay, but you could have A could map to B, but that point B could map back to another point in A, okay. Now it is a function, right, but it won't have an inverse, okay, because for each element A has got a unique element in B, but each element in B doesn't map back to a unique element in A, because that point there can map back to that point there, A, this value of A, and this can map back to that element of A, okay, so that wouldn't have an inverse, so f inverse wouldn't exist in that instance. Now let's have a wee look at that on the drawing package here. So we go back into this little drawing package and we'll bring it back up here. Let's see where it is. Okay, so let me see if we can draw out something. So if I put in, say that y equals x squared again, x squared, then this here won't have an inverse, okay. It won't have an inverse because when we go to the point, say 2, then we could go up to the point 4 there, okay. Now what we want to do is we want to come from the point 4 and then come back to this x-axis, but the problem is that when we're up at 4, once we get there, we can come back to that x-axis via two different routes. We can come back via that route there, which gives us -2, or we can go back via that route there, which gives us 2. So there's no unique route back from this y-axis to the x-axis. So if there's no unique route back, you can't find what the inverse is. It doesn't exist because you don't know what it's going to be, because you don't know how to go from this axis here back to that axis. Okay, so that's all the really want to say there about those inverses. So how are we going to find the inverse of a function? So let's have a look, and you can see you can work out kind of graphically. So if we had the function say y equals x, then what we could do is, if we wanted to find the inverse of that function, so what we'd be doing is we go along to say the point 2, then we map to the point 2. So if we come back again, 2 would still map to the point 2, and 3 we map to the 3 that way, 3 map to the 3 that way. So in effect this function here is it's a self-inverse, meaning that the function is y equals x. Well, the inverse of that function is x equals y, which is just the same function. But what if we've got something different? What if we've got something along the lines y equals 2x? Okay, so if y equals 2x, then what we'd be doing is we would go along 2 and we would go up to 4. But the new function, what we want the new function to do is, the new function, we want it to go along 4, but it would we want it from 4 to go to 2. Okay, in order to get 4 to go to 2, well, we could use the function y equals x upon 2. Okay, so you can see that there. So now let's just work through this. Let's say x is 2, so we go x is 2, and we're going through the purple one first, so we'll get 2 times x, which gives us 4. Now we want to get back to 2, okay, so what happens is we're now at the point 4, okay, and we get through the second function here, which is x upon 2, so 4 will then give us 2. So I'll read that through once more. We go from 2 to takes us to 4, and then we go from, in this function here, 4, which takes us back to 2, which is where we started. So this function here is the inverse of that function there. Now there's a wee little geometrical trick you can see. If I draw out the line y equals x, then in order to find the inverse of a function, what you do is you mirror your function on the line y equals x. So I've taken a mirror image of this line on this axis, which gives us this line here. Okay, and you can see that there. If you were to pick out a point, say up there and there, you can see that point there is equidistant from that line there, okay, along that straight line. So that there is a mirror image. So in order to get in order to find your your inverse, you have to mirror it on that line y equals x. Okay, so let's look at an example. Y equals 2x plus y equals 2x plus 1. Now we know we have to mirror it on this axis here, so the y equals x, I'll put in y equals x, so it gets mirrored in this line y equals x. Now so obviously when it gets mirrored, that point there is going to remain the same. We know that the gradient is going to be a half x, okay, but it's going to be a half x, and now we're going to have to change this as well to minus a half, so it's a half x minus a half. So let's put that in just to see. Y equals x upon 2 minus 0.5, let's put 0.5, okay. So this line here is the inverse, this line here, the orange line, is the inverse of the purple line, and you can see that it's been mapped, it's been reflected in this axis, the y equals x axis. Okay, now again, you just work through a few examples of that and it'll become more apparent. So also we can look at the composition of these. Okay, so we could look at, if we went from the function f of x, and then we looked at the inverse of that function f of x, will just take us back to x again. Or we had the inverse function of x, and we found the f of that function, it would just take us back to x again. So all we're doing here is we're saying that that's x and y. If we go through the function f of x, so we go from here to here, okay, through that function f of x, then we found the inverse of that. All the inverse would do, we just take us back from here back to there again, which is the function, give us the value of x again. So we're just going up, along, back down to where we started to get to the value of x. Okay, now let's see what else there is that we're interested in.